And maybe I shouldn't use the board, otherwise Patrick will go crazy with the light off. But this is basically the equation that we're going to deal with, that is giving us the acceleration between two masses, m1 and m2.
I can't see any of that.
Of course you can't. I should turn on the light, and then I'll shut it off for that. Let's do this. How about now? Yeah. So this was going to give me the equation for the evolution of the vector little r that connects two generic masses m1 and m2. And we said, this is little r, that if we choose a reference frame whose coordinate system has the center in m2, and we never change the orientation of those axes, so basically this reference frame that we called B is such that its angular velocity with respect to an inertial observer is constantly 0. If that is true, this acceleration is also equal to am1 in n minus am. Did I do it the other way? Yeah, m1 was the, yeah, I'm sorry. m1 was here, doesn't matter, but just to be consistent. m2 minus acceleration of m1. So that can be seen also as the relative acceleration between the two masses. So I can be sitting here, so this will eventually be a planet, and measure this vector and take its rate of change, and that will give me the relative velocity, and do it again, and that will give me the relative acceleration. So this is what will lead us next week, not Monday because it's a holiday, Wednesday, to define different types of orbits, which we're going to simulate today, at least one or two. That will be called Keplerian orbits. Okay? So we'll see how to characterize those, but as a student myself, I appreciated seeing, in some cases, almost like seeing the results first and then justify with equations. So that's what we're basically going to do. We're going to numerically integrate these, even though there are better ways to visualize those orbits than numerical integration. But it's part of this class is using MATLAB for astrodynamics, because in some cases you have no choice. You have to go numerical, and so that's what we'll do. Before we start, so this example here, by the way, you do have the code somewhere. I think if the library has the complete book online, there should be an appendix as well with code that you can probably just copy. I don't know if you can download M files, but probably you can copy paste. But I strongly advise against executing routines that are already made for you, because you just click run and you're not doing it. In the process of doing it, you see how to implement equations in code. Yes?
What's the B body for the omega B body?
The B?
Yeah.
That is what I'm calling this reference frame, in which the coordinate system that doesn't change orientation is fixed.
Okay,
The only thing that I know about B, I'm sorry?
that wouldn't necessarily, like that coordinate system wouldn't necessarily be the
No, it's not Newtonian. Not Newtonian, the inertial one. It's not inertial, because M1 can do whatever it wants. M1 can accelerate, it can go up and down, as long as the orientation of these bases doesn't change with respect to the inertial observer. We have demonstrated last time that this r double dot is also equal to this difference in acceleration between the two masses seen by an inertial observer, which is in general not the case. But if we pick that coordinate system that way, it is true. So we can do that. So as I was saying, also in homeworks, you should expect that I ask you to develop code by yourself. And of course you can copy paste from other sources, but even copying, it's an art. You need to understand what it is that you're copying. You need to know how to use it. Because if you do it blindly, chances are that you're going to make a mistake, or you have no idea what you're doing. So I'm not saying that you can't use code that is out there. I just am telling you that you should really understand every single line, and probably in some cases do it from scratch. And so we'll do it from scratch here. I mean, I have this thing already done. I did it before coming here, but I'll try to do it from scratch with you. So can you read that? Probably not. So this problem is, I don't know, I'll try this. Yeah, better, right? It's asking you to do the following. I can shut it off. Relative to a non-rotating frame, that's exactly what we did last time, of reference with origin at the center of the Earth. So now M1 is the Earth. A satellite weighing 1,000 kilograms, which is nothing compared to the Earth's mass. Position vector is R, 8,000 I plus 6,000 K in kilometers. So that is using a Cartesian coordinate that is not coordinate system that is not rotating and has the origin at the center of the planet. And that is the initial position. So that's your R0. And they give you the initial velocity vector, which is only on the y-axis, 7 kilometers per second on that axis. Use algorithm blah blah blah, we'll ignore that because we're not going to just do what it's done for us already. They tell you to use Runge-Kutta F forward method 4.5, which is the ODE 45 in MATLAB, to solve for the path of the spacecraft over the next, well, 4 hours. We'll do even longer than that. And then they ask you to determine the minimum maximum distance from the planet in that interval. Okay. So I have no idea why. I try to figure it out. I think this is just an error here. They go to solution. They tell you just grab that function and run it and stick these initial conditions. I have no idea where that 5 and 5 come from. I think it's a typo. I tried. You get just a completely different orbit. It doesn't work. So I think it's an error. I don't even know if this book has an errata coverage. Maybe it does. But I think that's just an error there. Because, of course, it's not the same. Okay. And they give you those answers. And if you stick the right initial conditions in there, it does work. So I'll just run what I have done, and then we'll try to build it together. And I know that many of you know how to use MATLAB, and many of you have used ODE 45, probably all of you before, but not for these equations probably. So at least we'll visualize what we'll formalize next time with Keplerian orbits. Okay, so this does a little more than what they're asking me. I'm actually integrating twice the equations of motion. I do it with Keplerian dynamics. I'll show you the functions and then we'll develop them. So this is the dynamics that is given by this equation here. The r double dot equals minus mu over r cubed r. And then, open, I added, no, not this one. I added the J2 perturbation, which is something we'll see in several weeks. But you can still simulate this stuff, and then we'll give the theory behind it. But it's a good exercise. What J2 is taking into account the fact that this planet is not a sphere. So this first function models exactly this dynamics, the one that we derived the last time, which is perfect sphere, uniform mass distribution, nothing else. J2 is a more refined model for the gravitational attraction. Again, we based forces on models, and we find out that they don't work that well. We try to improve the models. Well, this planet has oblateness. It's like a sphere that you squeeze at the poles. That's one of the things that we know. And so there is additional terms in the acceleration for r double dot that you can model with much longer equations. So I was trying to simulate that. And actually, I'll probably give you that as an uncollected homework if you want. So if I run this, and I'm running it for, as you can see, for example, 10 days. I didn't want to do just 4 hours. Unless it crashes, it should give me a plot. It may crash. Well, I've tried it before. It doesn't like the Wi-Fi, so if it decides that the license is not there anymore, it's just going to stay there forever. Okay, no, good. All right, so, yeah, it didn't crash. So the red one is the Keplerian dynamics. I don't know if you knew that you can do this in MATLAB. Just grab plots and remove them. Do you know this? No. And you can copy and paste in another plot. So that's encouraging you to cheat a lot, moving stuff around. You can do a lot of stuff. You can do crazy things with plots in MATLAB. So this is 10, what did I say, 10 days? Yeah, 10 days of that equation with those initial conditions just going around. As you can see, this repeats itself. I think I selected a very thick line to just see these against the blue, the other one. But it's basically on top of itself. And that's what we'll see starting next week, that from that simple equation, orbits just repeat themselves. They remain in the same plane unless they are parabolic or hyperbolic. In most of the cases where satellites go around a planet, they don't have to go to another planet. With that simple model, they remain the same. The shape is the same. It's like an object moving on a track. It just keeps going on a circle or an elliptical path. Instead, reality is at least a, what do I do now? Control V? I don't know. Control Z? It's gone. See. Let's see. Okay, it's back. So this is just 10 days, taking into account that that is not actually a sphere. You can imagine you can find images online. It's maybe like more like a football or an ellipsoid. That's what it is. The orbit doesn't sit in the same plane anymore, and that's only 10 days. And it's just modeling J2, and there is a lot more stuff happening than J2. So if you want, we can go a little longer than 10 days, just to give you an idea. You do a month, and your satellite, which is, by the way, in low Earth orbit, because with that initial condition, if you subtract the radius of the Earth, which is 6,300 something kilometers, it's pretty low. We're talking about a few hundreds of kilometers. Yes?
What does ODE 45 do?
ODE 45? Oh, you never used ODE 45. Really? How many have used it before? No one. I'm impressed. You guys have no requisites to take numerical classes before this?
No, I mean we have a numerical method, but we never use it.
I think you develop numerical methods, which is not the point in this class. So I'm not going to ever ask you to develop a numerical method from scratch, because even though I think they do in the book, I assume they would just use them for the purpose of simulation. This may be crashing now. So ODE 45, it's calling. Okay, so this is just to finish this comment here. This is after a month. This is what your orbit is doing. It's changing plane. It's not an ellipse anymore, staying there forever. As you can see, it is changing plane. It is doing something that it's probably not desired. So you can imagine how, if you put your satellite in low Earth orbit, you want that ellipse for some reason to repeat itself. You got to use some fuel there. You have to do something. Otherwise, the ellipse will not stay there by itself. Plus, I'm not modeling drag forces. I don't know what, I think the lowest point here, it's pretty low, maybe 400 kilometers, which means that eventually there is a drag force that can bring you down. So there's a lot of disturbances on top of the ideal orbit that comes from that you have to know and compensate for. So I just want to give you an idea here for what it means to be ideal and then a little more realistic. And this is just taking into account one effect. There is more stuff going on. So we'll create this. Okay, ODE 45. What does it do? Well, you go here and you ask MATLAB what it does. That's what you do. That's what I do all the time. If I have to integrate equations of motion and if I have to solve some equation, I don't, once again, I don't believe in memorizing stuff. I just use resources. I go and search. The ODE 45 solves differential equations, non-stiff differential equations, with the medium order method, and I think it's a Runge-Kutta method, the one that is mostly used in engineering. And here it tells you how to use it. You call that function ODE 45, as I am doing here. Where is it? Yes, one example is here. You have to call it on top of some differential equation. Okay? So this command at rel ACC, relative acceleration, is a function that I have created, and it's here, and we'll discuss it. So this equation, this function here, it's trying to simulate r double dot equals minus mu over r cubed r. And in t-span, you tell it what is the interval of integration. In this case, I go from time 0 to a final time that I'm defining here as 30 days. Y0 are the initial conditions that you assemble as a single vector. So here I am basically copying what the textbook gave me, 8,000, 0, 6,000 in kilometers for the initial position. and then 0, 7, 0 for the initial velocity. I think that's it. That's what they gave me. I should really try to use the board back and forth. If I turn on the light, this will just go away.
It shows up. It's just really faint.
Yeah. So, if you recall, at some point I said that this equation requires to integrate it an initial condition on position and an initial condition on velocity. So that is, in MATLAB syntax, is your y0. You put it together like this, right? Okay. And then you call that function. Every function in MATLAB has options. You can study the bunch of options that ODE 45 can have. You set them up. For example, in this case, I wanted the time step for the integration, for the numerical integration, not to exceed 10 seconds. You can do more or less, depends on how accurate of a simulation you want. Okay, so maybe I'm not going to recode everything since you guys haven't used ODE 45. It's worth just commenting my code to begin with. So good habit in general is when you create your code from scratch, comment it as much as you can. Because after a week, you'll open it and you will have no idea what the heck the code was doing. That's what happens to me all the time. I don't remember. It takes me a lot of work if I don't comment every line to figure out what I was doing. Because I come up with names for variables that probably don't make much sense after a week. So here there's not much in terms of comments, but at least I start saying this main file here integrates the equations of relative motion between two masses M1 and M2. M1 is the Earth, M2 is a spacecraft. And then I like to do clean the screen, close all pictures. I just want to have everything clean before I start. So these are my initial conditions. They were given to me. Is it coming? Okay?
Yeah, it's fine.
Okay. Position, as I said, velocity, and then you assemble them together. Now, if you assemble the initial conditions that way, that means what does that mean? This is also equal to R0 and R0 dot, right? That I need to create a function that represents how the derivatives of these evolve. So I want, in rel acceleration here, I want something that will output R dot and R double dot. How many have seen state space representation before? Okay, that's what I'm using, right? You probably have seen it in this form for linear equations, x dot equals ax. But you know, if you don't have a linear system, like in this case, this can also be just a generic function f of x, right? Where x is a vector. So in this case, my x vector is, well, it's y. It's 3 positions and 3 velocities. So I need to create a function that outputs r dot, r double dot. R double dot, I know what that is. R double dot is this, right? So let's go and look at that function. Questions so far? So I go here. Every function requires you to, call the output something. So I have I called it dy, derivative of y. And this is the syntax that ODE 45 will ask you to have. You give it a name, so you can call that John. It doesn't matter. It doesn't have to be relative acceleration. You pick that name. And then you have to have t, so that the ODE 45 knows that you are integrating with respect to time. And then u is the input to that function. Now these are all constants. The g that we've seen last time. M1 is the mass of the Earth I found in the book. So you can see it's 10 to the 24th kilograms. That's your satellite, 1,000 kilograms. Mu is g M1 plus M2. Okay. Now what is u? If I am working in Cartesian coordinates, everything that is in these vectors are x, y, z, x dot, y dot, c dot, right? So I do know already that this is, in Cartesian coordinates, is that constant over the square root of x squared plus y squared plus z squared cubed. And here I have xi plus yj plus zk. Correct? That is my r double dot vector. So I'm putting together this thing here. This is what I'm trying to spit out of this function. That the output of this function will be r dot and r double dot. Okay. The input instead, as you can see, it's basically y. It's not the derivative of y, it's y. Because x, y, and z are u1, u2, and u3. And u4, 5, and 6 are the time derivatives of that. Do you see what I'm doing here? If you do the substitution that I have there, x is u1, y is u2, z is u3, x dot is u4, y dot is u5, z dot is u6. All that function is doing, forget about the fact that I'm going to integrate it numerically afterwards. Just focus on this function. What that is doing is taking x, y, z, x dot, y dot, z dot at a given time, position and velocity at a given time, and it's generating velocity and acceleration at the corresponding time. So this is my input to the function. The output, what I call dy, is, what do I say here? I say that it's u4, u5, and u6. So that is, from here, it's x dot, y dot, z dot, right? I just take them from the input and just move them as the first three components of dy. And then that ugly expression there, which is just this, minus mu over the square root of the, it's the rate is r cubed times x, y, and z. So what I have here is x double dot, y double dot, z double dot. That is what I'm doing with that last instruction. You can stop me here and I can try to explain it another way. I really assumed that you knew ODE 45. I'm sorry. I don't know why I assumed that. But
I was just curious, did
yep.
you find before you got U6 in there?
The ODE 45 in here?
No, I mean the U4, U5, U6.
Yeah, you don't need to. You don't need to. This understands by itself, since basically it's built into the ODE 45. When you're going to call this function here inside ODE 45, the way you built it, since he has an initial condition of 6 components, it will go there and will understand the u has to be a vector of 6. And if you don't do it right, for example, say that I go back and I remove a component from the y0, it will return an error and will tell me the dimensions do not agree, something like that. So it's built into the ODE 45. It decides, okay, this is your initial condition, then I expect to integrate on a function that defines the differential equations where the dimension of the differential equation is 6. I expect 6 differential equations, and these are my differential equations. So ODE 45 takes this and computes it at every time step and integrates over time these 6 equations. So it integrates velocity to get me position. It integrates accelerations to give me velocity. Make sense? So this is just how you do it in MATLAB. So when you have a numerical integrator in MATLAB, the first thing you have to work on is, well, read the help, because that really helps. It's the help. So you really want to do that. And then there's no other choice than building your differential equations in a separate function like this that you have to organize these ways. Basically, the first components of the output are going to be the lowest time derivatives, and then you keep going. So here I have the x, y, and z with the dot, and then the double dot. Any other questions? I can probably, I'll put this in the canvas, my website, so you can grab them. But again, they are in the appendix of your book. There's plenty of these. But all these is defined here. Actually, I'm pretty sure that there is always an example here. There is always an example when you ask for help in MATLAB. So these are my equations of motion. These are differential equations, and outside I call them to integrate them starting from this y0, which is the initial position and velocity, and I tell the integrator to do it for this duration of time, and what this is going to give me as an output is, what I want is the integration of this. Again, when you integrate this, what you're going to get is x, y, z, x dot, y dot, z dot, which is your position and your velocity of the satellite around the planet. So the y out will be a matrix. At each time step has the corresponding position, x, y, z, corresponding velocity, x dot, y dot, z dot. And I don't think you have to call the output that way. That's a choice I have, t out, y out. So it's also creating a vector of outputs of times. I think you can call it without the t out, but I'm not 100% sure. Anyways, I always do it because it's convenient to have the time vector too. Okay, and all these options, I mean, the other thing you can do is help ODSET and figure out how many different things you can do with the numerical integrators, but it's really not for a class like this to describe how all these different settings can affect you. The one thing I can tell you is, in this case, let's go back to, I don't know, one day. Think about this. The satellite is moving at initial time at 7 kilometers per second. That should be the initial condition. So that's your time step. It means that this numerical integrator is computing that function that I defined there, relative acceleration, every 10 seconds. So it's integrating over an interval of 10 seconds. That's 70 kilometers of distance. I mean, on an orbit which is very long, it's probably okay. It looks like a straight line. But you can get to a point where the whole thing crashes. I don't know, 100 seconds is probably still okay. But you may start losing, it runs much faster, of course, but you start losing resolution. Because at some point, you don't know what's happening between two time intervals that are too far away. So this orbit probably lasts a few hours. Again, we don't have the tools to define the orbital period. We'll do it next time. I'm only numerically integrating these differential equations, but you can play with this, and you should see that at some point things don't look that nice. I don't know, let's exaggerate here, 1,000 seconds, I don't know what it will do. Yeah, even the red one starts becoming a little incorrect. Yeah, see the red is spreading, there is numerical error that you're throwing in. So these are the things that you want to play when you're not getting results that look very accurate. Okay, and so what I've done here with the second function is simply taking the same that I had before, identical. Up to this point it was just the same, Keplerian dynamics. And then I added this expression here, which it's an additional acceleration you get when the planet is an ellipsoid. And you can find, we'll get there. But I want to tell you where I grabbed it from. So this is a mistake. I didn't comment there where the equation is coming from, so I had to go back and check it. It's equation, at least in my version of the book, 1230. It's called the J2 perturbation. So it's a model better than this one for the gravitational attraction. There's nothing else than that. It's trying to represent a more realistic shape of the planet. And so I'll upload these. I'll upload all the three functions that I have here. But I do suggest that you try to do it yourself from scratch. You can actually start playing with ODE 45 since you don't have familiarity with it. Just with known simple differential equations, you can try to integrate x double dot equals kx. That's a perfectly fine differential equation. You can do that. Play with these ones, for which you know what to expect, so that you get familiarity with how to call the ODE 45, because we'll use it quite a bit. And that's not the only function in MATLAB. There's a lot more. Yes?
So when you integrate, you get out position and velocity of the satellite.
Yeah.
Do you graph the velocity over time to see like where it speeds up and where it goes down?
No, I don't have a plot. The plot that I show you is just a position.
But like, can you? Like, is it?
Yeah, you can.
Okay.
But you know, I can visualize in 3D a position. Plotting velocity, it's probably, if you want to see how it changes, maybe you want to do a plot of each component of velocity over time, because visualizing 3D velocity is not really helpful. So that gets me to the next part of this. I am plotting that sphere with the orbit around it. So what I did is, open a figure. Of course, I'm sure you've seen the plot3 command in MATLAB. So y out is, what I told you, is that matrix that has all the information that come from the numerical integration. So one thing you want to do before you plot something like that, you check how it's organized. It is 6 columns, 393 rows, and so 6 is the dimension of what I was expecting. So in each column, I probably have x, and then I have y, and then I have z, etc., right? So that's why, after I check the size, I go here, and I know that if I want to plot the trajectory in 3D, I am plotting column 1, 2, and 3, and that's what I'm doing, right? In a three-dimensional plot, I do it in red. I do it with a line width of 2. I don't know what that means. I just wanted to make it thick. I put a grid on, hold on, because I want to add more stuff to the plot. Axis equal, so that my sphere looks like a sphere. And then since I am actually, let me see. Oh yeah, I wanted to plot the initial position, initial position location. So I add another plot of just 1 point, the point at time 0, which is row 1, with the red star, so I could see where I'm starting from. And label the axis. The comment that units are important in your tests applies to plots as well. If you turn in any work where you have plots and you don't say what's on the axis, that is just a nice drawing that, a kid can do. There's no time, there's nothing, it's just a line. It means nothing. You have to put on the axis what's there. So here it's a position, so x, y, and z in kilometers. And I thought it was appropriate to have something representing the planet, because otherwise you just see this ellipse there. You don't have an idea of the scale. And so this command generates, I don't even remember what this generates. I just entered help sphere, and something came up. And it's a bunch of points distributed in space in a spherical way of unit. I think it's a sphere of radius 1. So you take that, multiply times the radius of the Earth, called the surf command, and that's what plots my strange planet that I have there. So my comment about using MATLAB is that MATLAB has pretty much a function for everything that you want to do. Everything is almost done. And if it isn't in MATLAB, there is a web page called, I hope I'm online. Yeah. Have you seen this? File. Have you ever seen this web page? So this is kind of dangerous. I have uploaded myself stuff here. So you have to trust the community and people that upload their own functions, and they promise that they do something, and sometimes they do, sometimes they don't. So I'm sure if you look for Astrodynamics, you can find stuff. I don't know. Let's see. And I'm not against you looking around for solutions. You can do this as long as, the Lambert's problem, this is something we'll see together. But you have to trust people who have created these functions. So again, my advice is develop your own software, because you can control your own software. If you use someone else's, it's a leap of faith. Okay, so what is it that we were going to do, though? I showed you all this stuff, but they really wanted us to do 4 hours, right? And I don't really care about J2, so let's remove this stuff that has to do with J2. Comment it out. What else? I think this does exactly what the problem was asking me to do. Yep, it doesn't even complete an orbit. I don't know why they chose 4 hours, but it's almost a complete orbit. Okay, that's my orbit. It goes around. What was the question? Find the minimum and maximum distance from the Earth's surface. Okay. How do you do that? I don't know. Let's see. I had a lot of commands that I should have saved somewhere else. Well, I know that my y out is my matrix containing everything, right? So, and you have to play with this. Norm, for example, the norm of, let's see, y out 1. I don't know if these will work. Maybe SQRT. 1 dot squared. Have you seen this before? It should supposedly square every single one. Let's see, 3. No. Thank you. 2. Okay, so this supposedly is going to give me the radius at each time step. So let's call this R. And let's not, well, let's see. I'm sure it will give me an error. It didn't. That's nice. Okay, now what is the max of R? Assuming I've done it right. Okay, that's the number. Now the height, the height. So I should do answer minus 6378. Okay. I don't know if it matches the what they have. Probably not. Maximum altitude is 9560 kilometers. Who knows? Yeah, that's close. I don't know what accuracy of numerical integrator they're using, but it looks pretty close to me. There is, you know, a change of what, 10 kilometers? Now, how do you know when that is happening? Because I know what the maximum altitude is, but how do you get when that is happening? You can do this. If I remember correctly, the max function and the min function actually can give you 2 outputs. Yep. The first one is, so R is a vector, right? I built that vector so that it's the square root, you know, the norm of all the positions. It tells me here the maximum value and where that is. So that's the index. What is the size of the vector? I think I went back to, yeah, it's more than 5,000 points. So at the point 2,974, that's what you get. And so to respond, for example, to this, which wasn't really asked, but they say the speed at that point is this. Okay. Well, what I will have to do is something similar to what I had before. Okay, let's see. This is going to be now 6, 5, and 4, right? Those are the velocities. And I'm going to do it at point B. Make sense?
What is that function?
Which one? The one I'm typing? This one? SQRT? Square root.
Well, no, I mean like the U out, the whole thing.
Oh, the y. No, that's so basically what I'm doing there is it's this. I'm trying to find the norm of the velocity at that particular time, which corresponds to the index 2,974. So that is the square root. What I'm doing is the square root of x dot squared plus y dot squared plus z dot squared, where these particular values are at a particular time. And since y out is the output of my numerical integration and the first 3 components are positions, the last 3 are velocities, I am calling the last 3. So the second index is the column, 4, 5, and 6. So that's x dot, y dot, z dot. And b because I called it B up there. It's telling me the location in the matrix Y out where I have the maximum height. So I just have B there. And these, let's not call it anything. Let's just do it. Yeah, that's 439, give or take. That's what it is. Okay. Well then, to complete, what do they want? The minimum. They want the minimum, right? So let's do the minimum too. Oh, I don't have to redo this. I have it already, right? So I'm going to do AB is now the mean of R. 10,000. Okay. So if I do A minus 6378, of course I wrote something else. 3,622. Okay, so this wasn't probably a low Earth orbit, so no drag here, because the minimum altitude above the surface of the planet is 3,000 kilometers, and usually low Earth orbits are, again, we'll formalize this, but you call LEO anything that is below 1,500 at the most, less than that, 1,000. So there's definitely not going to be any drag in this orbit because it doesn't go below this altitude. And they say that the speed is 7, so that is actually the initial condition, right? See if it's true. Where is it? At B equal 1, so it's, index is 1. It's the first instance. What is it? I lost it. Here. Yeah, 7. Exactly 7. So, before I play more with this, we have 10 more minutes if we want. Do you want me to go over anything again? There's no problem if you want me to. I don't know why I assumed you knew ODE45, but that's okay. We'll use it quite often, and I can post this so that you guys can play with it and build your own. No comments? Everything is clear? So the way I built this relative acceleration function is clear? Your goal when you have to integrate differential equations is that you create something that takes your state vector, that's what it's called, right? X, Y, X, where is it? X, Y, Z, X dot, Y dot, Z dot. That is what comes in as the U, and it assembles as the output the time derivative of the state vector, which is this, and that's exactly what that function is giving out. It's giving X dot, Y dot, Z dot, and the double dots. So that a numerical integrator can take the function and run it so many times so that it can build a time history. I can give you a lot of things to do with this once I post them. You can, for example, go ahead of the class and start looking at circular orbits and, for example, decide what is, so say that this is exactly the initial condition you have. And that's your velocity. What is an impulse, a change, an instantaneous change in velocity that you would need so that this orbit is not, because this is elliptical as we've seen, so that this orbit is actually circular? You can play with this stuff. You can go ahead and look at circular or elliptical orbits and imagine that's exactly what we do when we maneuver satellites with big engines. Imagine that you can change, without changing location, you can change your velocity in an instant. And so switch that 070 to some other value so that the orbit is not elliptical, it's circular. And you can play with this. Actually, one nice exercise could be this. What if I do 15 now? Kilometers per second. I don't think this is, see, it's going away. And it's not numerical error. This is probably a parabolic, hyperbolic trajectory. I don't know what it is, to be honest. I should do the math. Which we haven't done yet, but there are at some point you don't have closed orbits anymore. So this is probably going somewhere else, to Mars. I don't know. Or maybe I just don't increase it that much. I say 9 and it's a little more elliptical. No, it's still open. Or maybe it's not elliptical, I just have to run it for longer. So all these things will be able to answer them formally. Yeah, it's going away. Okay, it doesn't want to come back. But we'll be able to answer them formally without playing only numerically here, looking at initial position and velocity. Once you know those, you can tell me what is the shape of the orbit, if it's closed or not, if it's a circle or an elliptical orbit, etc., etc. So we'll see you next week. I will post this video next week probably. Okay? Have a good weekend.